Okay, all right. Well, I'm going to show you, this is an extra credit project that was given to me many years ago. And so what they did is they actually went to 3 different companies. And they went to 3 companies and asked them about, if I paid money to skydive with your company, what would I experience? So I'm going to show you some numbers here, right? All right, so she was pretty good how she did it. One color was one company, another color was another. So when you see the different colors, hang on. All right, how high do you go? Well, company 1 said you go 1,350 feet, 500 feet, sorry. The next company said 10,000 feet, next company 14,000 feet. How long does the skydive last? Well, even though this doesn't answer that question, they said you get 1 minute of free fall. That's a lot, and then you're going to pull the parachute. But then you're still going to take a long time before you hit the ground. And one of them says you get 35 seconds of free fall, and one of them says a minute. How long until you hit terminal speed? All right, it's about 3 or 4 seconds for one company, about 8 seconds for another company, and the other one said not long, so maybe they never figured it out. How fast are you going at terminal speed? And even though it depends on the surface of the person, they all said about 120 miles per hour. What was the landing like? Very easy, soft landing, rough, slippery grass landing. What's the fastest speed you'll go during the trip? Well, again, that should be at terminal velocity, shouldn't it? And let's see. How fast will you go when the parachute's open? And one of them said 20 to 50. Well, that's not good. Maybe they think when you first pull it out, you're going 50, but you better slow down to a lot less than that. One of them said 15. Now, I can't believe that third company did not know how fast you're going when you land. How long until your parachute's open? Again, that's about the same amount of time as free fall. Once they're done with free fall, they pull the parachute. And they say, that's enough because we want to make sure we have time for that to open. How long are you in the air with the parachute? So here's a company, I don't know why they said 1 to 6. That's a big range to me. One of them said 6, so even after you pull the parachute, it still takes about 6 minutes for you to come all the way down to the ground. And one of them says 3 to 4 minutes. Okay. Anyway, so one of them is called Skydive Carolina Skydiving, Skydive Rayford Invitation, and this is a guy, he actually did it, so she asked him to look that up for the company he had done. All right, what do you think about that? All right. Well, I'm going to show you today what we're, this is a book, and it was actually a translation of Galileo's work, and not that you don't probably sit around and read this kind of stuff, but I'm going to read something to you today. Wait till everybody's ready. Okay, wait a minute. Wait till everybody's ready. All right, so this is actually a translation. This is something Galileo actually wrote in one of his papers. If you know anything about the history of Galileo, there was a little battle between he and the Pope. He liked the church. He was okay with the church, but the Pope was convinced that some of the things that Galileo was saying were, he thought they were heretical, and that he was saying things against the church. Matter of fact, some of the things that he wrote, Galileo liked to write things in dialogues, and there was one person in a dialogue who kind of knew what was going on. The other person was kind of called Simplico, and he was the one who thought that didn't know really exactly what was going on. And the Pope was convinced, or other people convinced him, that Galileo was trying to portray the Pope as a simpleton. And that got him in trouble. Because if the Pope is supposed to be in control, or he had a lot of power back then, that's about the last thing you want to do is show that the Pope is, not smart. So anyway, I'm surprised some of Galileo's work was smuggled out. He was put on house arrest for the last 10 years of his life, and that means that, no, you can't go and publish some of your work and give it to other scientists, but luckily, I don't know the whole story behind that, but a lot of his work was smuggled out and was printed in another country. So we still have evidence of Galileo's work today. All right, here we go. Change of position. My purpose is to set forth a very new science dealing with a very ancient subject. That is, in nature, perhaps nothing older than motion, concerning which the books written by philosophers are neither few nor small. Nevertheless, I have discovered by experiment some properties of it which are worth knowing, and which have not hitherto, I didn't say it right. Good thing we don't use that word anymore. Have been observed or demonstrated. Some superficial observations have been made, as for instance, that the free motion, natural motion of a heavy body is continually accelerated. But to just what extent had not been announced so far as I know, and he thinks, and that's why he was given credit for discovering if something is falling, it has whatever it falls in the first second, it'll fall 3 of those, 5 of those. So he says, as far as I know, no one yet has pointed out that the distances traversed during equal intervals of time by a falling body at rest stands to one another in the same ratio as the odd numbers beginning with unity, meaning 1. 1, 3, 5, 7, 9. Okay? Now this chapter, he talks about this. This is this chapter. It has been observed that missiles and projectiles describe a curved path of some sort. However, no one has pointed out the fact that this path is a parabola. But this and other facts, not few in number or less worth knowing, I have succeeded in providing that I consider more important, that there have been opened up to this vast and more excellent science, and blah, blah, blah. Anyway, so he's trying to tell people about his discoveries, and this new chapter, chapter 5, is on projectile motion. Well, first of all, have you even heard that word before? Have you heard the word projectile? If you watch any kind of movies or something, have you heard that? So what do you think? Wait a minute. What do you think something is a projectile? Give me an example of a projectile. Yes?
Any thrown object.
Okay, a thrown object. What do you think?
Bullet.
A bullet? Okay. Have you heard about bullets being projectiles?
Yes.
Okay.
The slingshot.
Okay. All right. A rock in a slingshot.
Jeffrey, if you're wrong, he's a projectile object.
Okay. Anybody else? Wait. What else? What else?
A chunk of something flying through the air.
Okay. Okay. A chunk of something flying through the air. Hang on. Hang on. Hang on. Hang on. Hang on.
If I'm able to pick up Parker.
Yes.
Okay, hey guys, there's too much little small talk. Okay. Now, so I have a ball here, okay? So what I'm gonna do is, you can help me a little bit here. Get that out of the way. All right, so what I'm gonna do is I'm gonna take a ball and I'm gonna throw it. All right, here we go. All right, is it a projectile?
No.
All right, I'm not, is it a projectile?
No.
Yes.
So,
Be confident.
if we look at the real definition of projectile, it is an object that's been set into motion somehow. Whether somebody throws it, kicks it, uses gunpowder, whatever it is, it's in motion in air, isn't it? But the only force acting on it, of course, this doesn't count air resistance yet. We will count air resistance later, but not counting air resistance, a projectile, after it leaves my hand, or after it leaves the gun, what's the only force acting on it?
Air resistance.
No, I said it's not counting.
Oh.
We're not counting a thing. What is it?
Gravity.
Gravity. So now, wait a minute. Wait. Now, so here is this ball, and it's not a projectile because another force right now, the table pushing up, is another force acting on it, so it can't be a projectile. But watch. Now it is.
I knew it.
So as soon as it leaves the table, it becomes a projectile. See that? Okay, so I know. Here you go.
Projectile.
Go. Wait, now. Drill.
Yeah, I touched it.
Okay. Galileo said it had not been pointed out until he did it. Notice that he actually did some mathematics on this, that projectiles take on a path that's a parabola. Have you guys done parabolas in math?
Yes.
Okay.
Yes, we
So it has-
have.
So it has a parabolic path, but notice that when I did this, is that true? Is that true?
Yes.
If you jump, are you a projectile?
Say again?
Yes, I literally just said if I threw Jeffrey, he would be.
If you like jump in the
That's
air,
not
are you
jumping.
like a projectile?
Okay, now, if I, Even though it'd be a special case of projectile just to throw it straight up, that's a special case. But if you were to run and jump in the air, you'd become a projectile. Now, again, here's the problem, okay? And here's something I think Galileo was, I know he was a genius. When I rolled off the table, that didn't look like a parabola. It did. It was half. Wasn't it half a parabola? Okay, and so when I toss it like this, hang on, I toss it like this. Okay, watch now. Now what Galileo was able to figure out is, and this is what's amazing to me, and I think some of you don't understand this, that's why I'm teaching it, is that what is it about an object not traveling in a straight line? What is it about an object that's traveling in this parabolic path? And he said that there's only one force acting on it. Remember, a long, long time ago, Aristotle would have said, things don't move unless you push them. And some of you still think that. Galileo said, no, once it's in motion, it has a tendency to stay in motion, and you don't have to push it. And so Galileo would have said, when you throw that ball like this, what makes it keep going this way? What force?
Inertia.
But inertia is not force. But inertia is why it keeps going horizontally. Now, what happens to the ball vertically? The same thing you learned last chapter. Watch now. Constant deceleration, acceleration. Decelerate, accelerate. Put them together, put them together. So what's happening? What's happening to the ball? What's happening to the ball horizontally? Everybody look at me. What's happening to the ball horizontally? I could look at a picture of somebody shooting a free throw, and I had a grid behind him. What would be happening to the ball just horizontally? Don't worry about up and down. What's the ball doing horizontally?
It's going in the direction.
Thanks. Somebody who wasn't in physics at all would tell me that. How about, using physics lingo, what's the ball doing horizontally when you shoot a free throw? Yes?
It's staying at a constant velocity.
Yes, because that's what inertia says. I have a tendency to keep moving in that direction in a straight line at a constant speed. Now, the reason I'm not going in a straight line is because there's another motion occurring, isn't it? And so Galileo, pretty smart, he said, what's going on vertically with a free throw shooter? A free throw shooter, what's the ball doing vertically? It's going like 5, 3, 1. 1, 3, 5, 7. See that? So he said, what's that called? What is a physics student going to say? How would you describe a motion vertically if it went 5, 3, 1, 1, 3, 5? What's that called?
Inertia.
Okay, again, we have this, you're just forgetting it. That's called constant acceleration. And so here's what Galileo, this is where he made, I don't see how he figured it out. He said, a projectile has two motions occurring simultaneously. What's that mean? At the same time?
Same time, yeah.
But he said they were independent of each other. Now that blew me away. When I first learned this, it blew me away. He said, it doesn't matter. It doesn't matter how fast you're going that way. It doesn't matter how fast you're going in that direction. Whatever you do here, if I throw a ball, if I throw it really, really far, like if I throw it from out left field to home plate, and my ball went 30 feet in the air, okay? And I threw it really fast, and it went 30 feet in the air, all right? Which ball stays in the air longer, that one? Or if I stand here and just do this and throw it 30 feet in the air?
193. Well, I guess you both throw.
And I'll tell you what's amazing. He said, it doesn't matter how fast you throw it that way. If it goes 30 feet in the air, it's only going to spend so many seconds going up and so many seconds going down. And so which ball is going to spend more time in the air? The one thrown fast from left field or the one that's going like this? They're the same.
They're the same. I knew it.
Wow, that's amazing. He did that. The other thing I found out one time in a physics class long ago, and I guess I have a certain amount of, ego, like some of you guys do.
Swag.
All right. And so I remember a physics person saying this, and I guess I had enough pride to say, well, you know what? I think they're lying. That's a lie. I just thought there is no way, because my mind my mind at that time couldn't conceive of that. Here's what they said. If you had a rifle sitting parallel to the ground, and a high power rifle, okay? And what happened is, at the very instant that the bullet comes out of the muzzle, at the very instant, another bullet sitting here on a little tray will fall. You ready? Boom! And which bullet will hit the ground first? And I couldn't, at that time, many years ago, I couldn't wrap my mind around it. So what's happening to the bullet that's right here? It'll go accelerate, won't it? Let me go, 1, 3, 5, 7, right? What's the other bullet gonna do? Whoa! That horizontally, it's gonna be going like that. But what's he doing vertically? What's that bullet doing vertically? 1, 3, 5, 7. And both bullets will hit the ground at the same time. I had trouble wrapping my mind around that because my mind kept saying, but the bullet's going so far. You know what my mind wouldn't let me do? It wouldn't let me say, but he's gonna get there real fast. Oh, that's what I could see. That's why I had trouble. Because my mind kept thinking, it's so far, there's no way that that's gonna hit the ground at the same time the other one. But it's so far, he's gonna get there really fast, isn't he? And they're gonna spend the same amount of time there. Now, if you go home and somehow in dinner this conversation comes up, don't tell the story wrong. Number one, if you point that gun up in the air,
Then I want.
the other one will lead it. If you point it down, boom, that one will win. You get it? If it's level with the ground, then the two bullets will hit the ground at the same time. Now what I do, I'm not set up today for that, but when you come back on Thursday, I have a couple demonstrations that I'll show you. I don't have a real gun, but I have a little device that is a spring.
Shows up.
I do have a gun, that's I'm bringing to school. But anyway, when I have a little device, and it has a ball, and it has two balls in it, and it has a little trigger mechanism, spring loaded. And what I'll do on Thursday, I'll show you, I'll pull the trigger, and one ball will fall straight down, and the other ball will get kicked out, okay? And what we'll do is I'll have two tables set up, I'll be up on a ladder, and then you'll have to tell me which ball hit first. And when I do that, do you think you're gonna hit bang, bang, or you're gonna hit bang? And it's hard to believe that the ball that goes straight down will hit the table, will spend the same amount of time in the air as the one that gets kicked out and takes the parabolic pad. And that's what Galileo, he said, there's two motions occurring simultaneously, but they're independent of each other. That's another thing I had trouble with. So I played a lot of baseball and softball in my life, and a lot of times I spent out in left field. I actually could throw the ball pretty well, and I could throw it to second base, home plate. And I just thought to myself, if I throw it fast enough, it's going to spend more time in the air than your ball. But actually, it depends on how high it is. If I throw a ball and it goes only 30 feet off the ground, and you throw one not so fast and it goes 30 feet off the ground, they'll both spend the same amount of time in the air. This cannot affect gravity. The inertia cannot affect the Earth doing its thing. Can you remember that? All right, this right here will not affect the Earth. You can't say, hey, little g's, not little g's, you throw something really fast. That'd be kind of silly. That doesn't work. All right, let me, whoops. Be sure everybody on this half of the room. Hey. All right, what I could do is, if you have some kind of a pen, I have this little grid I'm going to show you. I'll show you a little grid here.
This man just walks around the swing.
All right, thanks. Thank you. All right, need everybody's attention up here, okay? You know what I saw yesterday? What I saw yesterday is that some of you struggled with some of the parts of the worksheet. And some of you are struggling like with something that you supposedly learned before. If delta V over T was velocity, then why did we not know how to do that? Some of you, if F equals ma, how do you rearrange that equation? Some of you were showing me that a skill like a pre-algebra skill, you didn't know how to rearrange an equation. And that's some of the things you've done before, so you got to be careful about those things. So sometimes it's details. Sometimes it's little details, and you're missing some. All right, so let's take a look at this. Now, I have a grid here, and what I'm going to do is we're going to put a dot down here. Everybody ready? Okay, now, what I like to do is I'm going to go up 7 blocks. I'm going to go 1, 2, 3, 4, 5, 6, 7. Okay? And now I'm going to put a dot there. And then I'm going to go up 1, 2, 3, 4, 5. And then I'm going to go up 3. 1, 2, 3. Then I'm going to go up 1. Okay, now what did I just draw a picture of in physics? If you're a physics student, what do you see there?
Odd integer pattern.
What is it?
Odd integer.
Well, what is that about? What does odd integer pattern show you?
Acceleration.
If it's on a ramp, what does it show you? If it's in free fall, what does it show you?
Free fall. Constant.
If it's on a ramp, it's not free fall. Constant what?
Acceleration.
Right.
Near it.
Now, see, we should know that. Everybody in this room should know that if something's under constant acceleration, that's the pattern it's going to have. So if I throw an object up, it's going to be going really fast at the beginning, right? And let's say it's going, I don't know, 40 meters per second. Then what's it going to be going? 20? No, 40, then 30. 30, then what? 20, and then 10, and then 0. But wait, on the way back down, 0, 10, 20, 30, 40. Everybody get that? So the picture going up is the same as the picture going down, isn't it? So one more time, I drew a picture of constant acceleration. In this case, it's acceleration due to gravity. That's why I call it little g. So a projectile, once it leaves my hand, it becomes a projectile. The only force acting on it is gravity. Oh yeah? Well, why does it keep moving this way then? Why does it keep moving this way? So let's draw a picture, and I'm going to pick a number. I'm just picking a random, and I hereby declare that you're going to go 2 blocks a second. 2 blocks, 2 blocks, 2 blocks, 2 blocks, 2 blocks. Okay? What is that a picture of? If you're a physics student?
Speed.
And let's wait. Wild guessing is. There's a time for that, but what do you think? What do you think this is? You say, I went 2, I went 2, I went 2, and every second I went the same amount. What is it? You ready now?
Constant speed.
That's right.
Let's go.
Now, wait a minute. I know that constant acceleration is due to gravity, but why did you say constant speed? What's the cause of that?
Because it's equal distance and equal.
What's the cause of it?
Oh no.
What do you think? Inertia.
Oh. I
So,
saw an answer right there.
Even though, wait a minute. So if I throw an object like a baseball, or I shoot a free throw, why does the ball keep moving horizontally at a constant speed? Inertia. Why does the ball keep decreasing its speed at a constant rate and then increasing its speed at a constant rate vertically? And that's because of little g, isn't it? Now let's put them together. Here we go. Just like Battleship. Ready? 0, 0. 1 second later, horizontally, you have to be here. 1 second later, vertically, you have to be here. I guess I'm here then. So I moved this way and I moved this way. 1 second after that, I have to be here horizontally and I have to be here vertically.
Why if it's not constant speed?
Let's keep going. What now?
Never mind.
1 second later, I have to be here horizontally and I have to be here vertically. 1 second later, I have to be here horizontally and I have to be here vertically. Is everybody with me or not? Am I going too fast? Okay, now 1 second later, I have to be here horizontally, and ooh, I'm back down here. And then 1 second later, I'm here, and I am here. And 1 second later, I'm here, and then I am here. And 1 second after that, I'm here. Now, if you think about this, this is something you already know. We're just putting them together. Galileo was able to put this together and said, there's two motions occurring. Here's right here. There are two motions occurring simultaneously, but they are independent of each other. And the two motions are constant acceleration vertically, constant speed horizontally. Now, watch what we're going to do here. We're going to connect them now in a nice smooth curve. And what shape do we get? A parabola. Now, if you happen to have another color pen, you can, or if you don't, just kind of make it look different. What I'm going to do is I'm going to change one thing. I can't change little g. But what if I kick a soccer ball one way and I kick a soccer ball another way? It'll take a different path. So let's pretend that we want to go, let's make up a new number. You want to go 3 or 4 units. Which way, how many you want to go horizontally? 4? Okay, I don't want to run out of space. I'll do it anyway. 1, 2, 3, 4. Okay, so I need to be here. Okay, and then 1, 2, 3, 4. 1, 2, 3, 4. 1, 2, 3, 4. Okay, and we'll see what happens here. 1, 2, 3, 4. All right, now let's try it. Ready? 1 second after I launch, I have to be here horizontally. I have to be here vertically. And then I have to be here and right here. And then I have to be here. And what's my third location? That's up here. And then I have to be here. And my next location is right there. And I'm just trying to match these up, right? So I'm going 4 blocks horizontally every second. But I can't change that, so I still have to match up here. Now keep going, 4 blocks. I'm going to run out of, that's all right. And I can probably get one more in there. Wow, okay, so now let's see what happens. Does this make sense to you that I can't change what the Earth does to a ball vertically, but if I were to give something more horizontal speed, does it make sense to you that the path is going to look different? So you can have different kinds of parabolic paths, can't you? But they're all parabolas, aren't they? All of them are parabolas. And I think that's what Galileo, that was a genius for him to be able to figure that out. I'll show you a quick drawing here. Okay, this is something else that Galileo figured out. And by the way, I'm not gonna tell you that Galileo was not human. Galileo, he had to have some place to live. He had to have food to eat, right? But he was pretty smart.
Right.
And so back then, if you were a pretty smart person and you invented things or you seemed to have more knowledge than other people, there were people like kings who would make sure that you had food to eat and stuff like that. But I might ask you also to do something for me. Get that? Galileo, for example, had a lot to do with the making of cannons. He knew enough physics about cannons. When you take a piece of steel and you said, I got to make a place to put the cannonball, and you just start drilling into that, there's so much heat that's produced, it would crack the cannons. So he figured out a way to be able to bore holes in for make a cannon. And so they made good cannons. Now, the next thing you want to do is, I have a nice cannon, right? And there's the enemy right there. Boom! It's 100 feet short. Boom! It's 300 feet too long. And so what he did is he figured out the physics of projectiles. And so he actually helped them, they would train them and teach them how to shoot those cannons and more likely to hit the target. Does that make sense to you? So if I'm going to shoot 10 cannonballs and 8 of them hit their target, That's going to be more effective than somebody who doesn't hit, only hits 1 or 2. So here's what he found out. Now this does not count air resistance. I'll show you air resistance in a minute. Not counting air resistance. He figured out if you were to kick a soccer ball or shoot a cannonball at a low angle, 15 degrees, how far down range would it go? Not very far. Why not? A 15-degree angle, and I kicked it, why wouldn't it go very far? Help me out. Why didn't it go very far down range?
Because it didn't go up that high.
And when it doesn't go very high, what does that mean?
It doesn't go as far.
Why not? Well, you're getting there. Why not? Ooh, you're so close. You're so close.
Jeffrey.
If I'm moving at 20 meters per second horizontally, what if I'm in the air for 1 second? I'll go 20 meters. Well, what if I'm going 20 meters per second, but I'm only in the air for half a second? And I'll go 10 meters. So why does this ball kick at 15 degrees not go very far down range?
Because you're not in the air for that.
That's right.
Let's go.
Now, next, watch what happens. If you change the angle to 30 degrees, notice that you go further down range. Everybody see this? Now, that's because you spend more time in the air, but I'm not really worried about up and down. If you have more time in the air, then horizontally, you're going to go further down range, don't you? Now, what about 45 degrees?
You got the farthest.
Okay? And then we might as well go to 60, and if we go to 60, it's going to go even further, isn't it?
Oh,
No. Whoa. Here's what Galileo discovered. If you shoot it at 60 degrees, it's going to come down the same place as when you shot it at what?
30.
You said, what's going on? I spent even more time in the air. You did, but you know what? Because it went this much, so much, not much of your component was going this way, was it? You weren't going horizontally very fast.
So we'll always go the furthest at 45 degrees.
Yes? Now, but else, what else he discovered is that one shot at 75 degrees would land the same place as what?
15.
And one shot at 60 lands the same place as 30. And if I ask a test question, I'll say one shot at 20 would land the same place as what? And some of you don't see the pattern yet.
What's 20? Oh, what? Oh, no, it's it equals 90, so it's 70.
Yes. He said that not counting air resistance, that the complementary angles will land downrange in the same location. Now that's again, I've seen some things with Olympic training camp. So we have some Olympic training camps in the United States. One of them's in Colorado. And they are very sophisticated, very scientific. First of all, give me the best athletes and send them there, and I'll make them better. And what they do is, and I've actually seen this, even at High Point University, I've seen them. They have a sports development place over there, and they put a whole bunch of dots on the person, and then the computer keeps track of those dots and makes a graphic of all those dots. Okay, now, what happens is, let's say you're a shot putter, and you have the way that won you the state tournament, the way that you and they say, but we want you to win the Olympics. You got to be better than a state tournament winner. And so they watch you on physics, and they watch all the dots, and they really are watching the ball also. And when you get ready to launch that shot put, ready? Once it comes out of your hand, it becomes a projectile, doesn't it? And what they do is, okay, now, they'll measure the angle. They'll measure the angle at which that thing come out of your hand. So here's this, right? Ready now. Now, let's say you're throwing it at about 30 degrees from here. Well, then you're not maximizing your distance, are you? So they retrain the shot putter to show slowly, we got to make you do a little differently. Now you're up to 40. Now you're up to 45. Actually, in the real world, because of air resistance, they train them to go at around 47 degrees. If you go 47 degrees, even counting air resistance, if two people have the same strength, and you shoot it at around 47, they shoot it like at 35, you're going to throw it further than they are. And that's how you win the shot put, throwing it down range, don't you? Now, it is true that Galileo was smart enough to also figure out what about air resistance, and it is true that the real path is going to be shorter than that, but he made adjustments for that, and that's how they figured out how to shoot the cannons that way, right? Well, anyway, there's a lot of neat stuff here. It's stuff you know, you just have to put it together. Okay, everybody right? All right, well, thank you very much.